not only good amount of research, but good number of researchers in India also. So now Lakshmi Bala is a person who started with particle physics, pretty much like me. Then out of curiosity and mathematical inquisitiveness, got into coherent states, quiz states, basically non-classical states of light. And then using Wigner function, fractional arrival to characterize them. And now she's into quote unquote hardcore experimental stuff, like you can see optical tomograms. And so without much ado, I will request Professor Lakshmi Bala to take over and talk about this optical tomogram and its connection. Basically, very comparing probability distributions, it has very close connection with experimental things. So please go ahead.
Thanks, Professor Panigrahi, for this very kind invitation. I have definitely been associated with QIQT, I think, since its inception. And of course, in the pre-pandemic days, it used to be a pleasure to go there and be in Kolkata and enjoy the atmosphere, a very vibrant atmosphere there. Of course, during the pandemic, I certainly appreciate the fact that the QIQT workshops continued online in a very, very intense fashion. And I have sat through some lectures whenever I could find the time and learned a lot from them. So now, of course, we have seen the advantage of the hybrid mode. And although physical presence is not required, it is very nice to know that the QIQT organizers have really become very, very professional at conducting this workshop, and it's of a very, very high caliber. And I learn a lot by attending this workshop. I thank the organizers and Professor Panigrahi. And since I'm not seeing you, and since I have a power problem here, can you please confirm that you can hear me?
Yeah, we can hear you pretty loud.
Okay, fine. So I want to start with the quotation from Rosenfeld, which is put down there below. It's from the selected papers of Leon Rosenfeld, and the editors are Cohen and Stachel. He says, Schrödinger made no secret of his intention to substitute simple classical pictures for the strange conceptions of quantum mechanics, for whose abstract character he expressed deep aversion. Schrödinger was not the only one. All of us know that the history of quantum mechanics, the early history, has been very tumultuous. And there have been a lot of arguments between the best and brightest physicists the world has ever seen in understanding the surprising elements of quantum mechanics compared to the classical world. And therefore, one would like to think, why not push whatever we know from classical physics to understand the quantum domain? How far can we do this? What am I doing now? Okay. So one of the main problems in quantum mechanics is this. Why can we not do quantum mechanics with classical probability theory? After all, quantum mechanics is inherently probabilistic. And classical physics, long before one worries about classical physics, there is a lot of mathematics. Probability theory was an already extensively studied branch of mathematics. So why not use the laws of classical probability theory to look at quantum mechanics? To what extent can we use the laws of classical physics here? Now, it was in that context that Pauli asked this question. Suppose I gave you modulus of psi of x the whole squared, which is the positional probability density, and of course, modulus of psi tilde of p the whole squared, which is the momentum probability density. Suppose I gave you these two alone. can we reconstruct psi of x and psi tilde of p uniquely? Uniquely is important. You can't measure the wave function, but I give you these two probability densities in the conjugate pair x and p. Now, the answer is trivial. In doing the mod square, the phase information is lost. I should be able to reconstruct psi of x and psi of p apart from a phase. What is the problem? The answer is no. Now, this question was raised by Pauli in Handbook der Physik. You can always give a trivial example. You lose the phase information, and therefore the answer is no. But a non-trivial example actually comes by examining two squeeze states. And this is put down in Reichenbach's book, Philosophy of Quantum Mechanics. So he gives you two states, wave functions, psi1 of x and psi2 of x. Now, the normalization is the same. You define an alpha and a beta. If beta real, so beta is beta star, and alpha, real alpha is greater than or equal to 0, you have this x squared term and the x term. And these two look somewhat similar to each other, psi1 of x and psi2 of x. You can find the corresponding psi1 tilde of p, which is put down there, and a psi2 tilde of p. Now, if you look at mod squared of psi1 of x, it will be the same as mod square of psi2 of x. I don't know if you see my arrow. Do you see the arrow that I'm moving here?
Yes,
Perhaps.
we can.
Okay. So the mod squares are the same. So I have given you two wave functions whose mod squares are the same. And if you look at psi1 tilde of p the whole square and psi2 tilde of p the whole square, the mod squares are the same. However, it is not as if psi1 of x and psi2 of x are off by an overall phase. If you look at the fidelity, which is the overlap of psi1 with psi2 mod square, this quantity is not unity. So we are not now discussing the trivial example of something being off from something else by an overall phase. We are looking at two different states. So the original question, if I give you the two probability, if I just gave you these, can you reconstruct the states uniquely? You cannot. And in fact, these two states, you can look at their squeezing properties, and you will find that they are both squeeze states in one of the quadratures. In fact, this kind of state was experimentally seen later by Slusher in his experiments on atomic vapor. So this is a good thing to learn. One can never say two wave functions can only be off by an overall phase to give the same probability density. This question of Pauli's has a lot of connection with tomograms, and I will get to that later. But I just want to recall that there are different approaches to understanding the quantum classical divide. And optics provides a very ideal framework for investigating the links between the classical and the quantum, overlaps, differences, and so on. And as I said earlier, probability theory is extensively used in classical settings. And since quantum mechanics is inherently probabilistic, why can't we do probability with quantum mechanics? The problem is, once you take the experimental data, which comes in the form of tomograms, and then create the state, you reconstruct the state. And since we are going to work with optics, if you look at different states of light, many of you among the students may already know that the state, or equivalently the Wigner function, is quasi-probabilistic. Because if you plotted the Wigner function, it's a function of x and p. I mean, in the xp plane, if you plot the Wigner function, there are regions in the xp plane where it is negative for many states of light. where X and P are the field quadrature operators, not to be confused with position and momentum. So clearly, this whole business of trying to apply classical probability theory in quantum physics does not work too well with Wigner functions. But suppose we identify a probability distribution or a collection of probability distributions, which we shall call the tomogram. These are not quasi-probability distributions, and attempt to understand different states of light. We should be able to see differences between the classical and the quantum approach. So that is the philosophy of this kind of research. So what is the tomogram? First of all, in an experiment in optics, the data available from measurements on the field state, you bin it into histograms, and it's called an optical tomogram. Now, the way it's done is essentially like a medical scan, which you see in hospitals. So at different angles, which I will call theta, you get hold of the probability distributions and put them all together, the intensity distributions. In the medical scan, they will call it intensity distributions. And you put them all together and the image comes and you see what you understand about whatever you're studying. So at different angles, an output image is obtained, and each image is a slice of the full tomogram. Each image therefore carries partial information about the object. Now, state reconstruction means the full state is to be reconstructed from this set of all slices or images. It's obvious that since one also talks of medical scans, the reconstruction could be in the classical context or in the quantum context. In the case of light, quantum context means treating light as photons. Now, there is an interesting question. In practice, you can only do imaging or scanning over a finite set of angles. So only a finite number of slices can be obtained. But in principle, we may need an infinite number of slices to reconstruct the object. So important questions that rise are, what is the optimal number of slices needed to reconstruct the object? Now, the number of slices clearly depends on the system considered. But in physics, we can ask, can there be any favored set of slices? Perhaps the slices corresponding to canonically conjugate variables, such as position and linear momentum, or if you're talking about light, the field quadratures. An allied question is, state reconstruction is messy. You see, it's all very well if you just deal with, finite dimensional Hilbert spaces, like 2 spin halves or 3 spin halves or something like that. But you see, in optics, the moment you mention light, you've already moved to an infinite dimensional Hilbert space, and you're talking continuous variables. We are not talking about the polarization states of the photon. We are talking about field quadratures. And then you see, you can't do experiments or measurements over an infinite number of slices. And with the finite number of slices, can we avoid detailed reconstruction of the object and infer its properties? That means take a tomographic approach. After all, we do that in a medical scan, where even qualitative features and changes are compared to a reference scan, and this becomes important. So basically, here is a flow chart. You start with the experimental data in the top left. From the data, you construct this quadrature histogram. That means you bin the data, and you get the optical tomogram. You can either read off as much information as possible about the state directly from the tomogram, or you could go through a very complicated statistical procedure, which is inherently error-prone, and try to get hold of the Wigner function. Makes more sense to try to work directly with the optical tomogram for a variety of reasons. The first reason being that the tomogram only comprises of good blue-blooded probability distributions. There is no quasi-probability there. And therefore, at the level of the tomogram, you might be able to push the laws of classical physics and understand something about the state. The other thing, of course, as I told you, with unknown states of light, and there are a whole lot of them, state reconstruction becomes a mess. You're dealing with infinite dimensional Hilbert spaces. So just to get our bearings straight, the birth of quantum optics is simply in understanding that there is a big connection between these two quadratic forms. In the case of the oscillator, the form was quantum oscillator. It will be x squared plus p squared, where x is position and p is momentum of the operator. I have stripped off all the constants, the m and the omega and all that, and compare it with E squared plus B squared, which is the electromagnetic field density, energy density. So you could use the A and A dagger of the harmonic oscillator, except that you will reinterpret A as the photon destruction operator and A dagger as the photon creation operator, A dagger A as the photon number operator, and this ket n out there is an eigenstate of A dagger A, but it won't refer to the nth level of a single simple harmonic oscillator. It will be the n photon state. So you have already moved very nicely to multi-photon states, where n represents the number of photons in a state. The field quadrature operators are no longer called position and momentum, but they bear analogous definitions to position and momentum. And you will write the operator x as A plus A dagger by root 2, and p again as A minus A dagger by root 2i, the same way as you do for the harmonic oscillator. There are different types of states, and I'm just recalling for you the standard coherent state, which is an infinite superposition of the Fock states or the photon number states n, but weighted with a very, very specific probability amplitude, where alpha is complex. And of course, this represents to ideal coherent light. As in a medical scan, we normally use this as our reference state. It is also well known that this state can be got by a unitary transformation on the zero photon state. It's an eigenstate of the photon annihilation operator, and it satisfies minimum uncertainty product in the field quadratures. So you say that a state is squeezed in X if the corresponding variance is less than half, and similarly in P. Of course, everybody has heard of the squeezed vacuum. That one is an infinite superposition of the photon number states, including the zero photon state. But I can give you another example. This is a finite superposition, root 3 by 2 ket 0 plus half ket 1. It's just a superposition of the zero photon state and the one photon state, and it is still squeezed. Of course, you have heard Professor Agarwal recently, and of course, you have heard him in many contexts. It is certainly to him that we will attribute the first theory paper on photon-added coherent states, where you repeatedly apply a dagger on the coherent state, standard coherent state. And if you did it m times and normalized it suitably, you will get the m photon added coherent state. By the way, it also happens to be an annihilation operator eigenstate. And this is the form of the annihilation operator. And I do not know if Professor Shivakumar is in the audience, but I believe this was something that he put down in a paper first time. Now, I have been saying all sorts of things. First, I told you about the Pauli problem. Then I just moved on to states of light and so on. What has the Pauli problem got to do with all this? Pauli's question has a lot to do with tomograms. So I formally defined the tomogram the tomogram x theta can be written as a dagger e to the I theta plus a e to the minus I theta. Recall that we need to do our measurements at different angles, and this is how the angle is modeled in. Of course, if e to the I theta is 1, and so is e to the minus I theta, you get the field quadrature x, or we might call it loosely the position quadrature, which is a plus a dagger by root 2. And if theta is pi by 2, you will get the momentum quadrature. So how do you get the tomogram? You don't know the density matrix, but suppose it is the density matrix for a pure state. Then this tomogram is simply the expectation value of the density matrix for a given theta in the state x theta comma theta. So it's obvious that if it's a pure state, and you can write rho as psi psi, ket psi bra psi, the tomogram is the mod square. You're writing psi in the basis x theta comma theta and taking the square. This object, this ket here, x theta comma theta, is an eigenstate of this operator, which I have put down above. So clearly when theta is 0, that operator is the position operator. And when theta is pi by 2, it is the momentum operator. But again, I repeat, I may call it position and momentum, but they are the field quadratures. The important point to note is this. You first fix your theta. Then the x sub theta corresponding to that theta gives you a complete basis. In particular, you would get the position basis and the momentum basis corresponding to theta equal to 0 and theta equals pi by 2. And you can always go from ket x to ket x theta comma theta by using this unitary operation, e to the I theta a dagger a. Now you know where I'm heading. But before that, let me give you a picture of a tomogram or some tomograms. The top left corner A is the tomogram for the coherent state. The plot is always theta along the y-axis, x theta along the x-axis. If you freeze theta, you get a complete basis x theta. So fix your theta, go along the horizontal, and you get a complete basis. And the tomogram is simply the modulus of psi squared in each of these thetas. So that's your color code out here. If I take this tomogram and reconstruct and get the Wigner function, that is done through an inverse read-on transformation, this is the Wigner function. For the coherent state, of course, there are no negative regions of the Wigner function in the XP plane, but that's not true in general. Just for more demonstration, I have put down here the optical tomogram for the even coherent state, which is a superposition of ket alpha and ket minus alpha. And here is the tomogram for the odd coherent state. So with this in mind, we go to Pauli's question. Suppose I were looking at the x basis. That means I set theta equal to 0. Do the tomograms W of x and W of p for theta equals pi by 2, do they suffice to reconstruct the density matrix? That was Pauli's question. So what is it that is being given? You're given the diagonal elements of the density matrix in the position and the momentum representation. Is that enough to construct the state? So Pauli's question translates to tomograms in this manner. Now, it is not surprising that you need the off-diagonal elements. Even in the earlier example that I gave with 2 squeeze states, it was clear that this is not sufficient. In the context of the tomograms, it tells you that the off-diagonal elements in a given basis, that means you need terms like psi of x, psi star of x prime. These can be got only if you invoke all the marginal distributions. That means you have to integrate the tomogram over all theta and over all x theta. The explicit expression for rho of x prime, the XX prime element of rho, for instance, is given in this, and it's a very, very nice paper. In a more general setting, I wrote a dagger e to the I theta plus a e to the minus I theta. Instead, you could have a changed notation, which is what is normally used in classical tomography. You talk of P and Q, and you have two real parameters, mu and nu, accompanying them. And so you have the position basis and the momentum basis. The tomogram is now a function of mu nu and maybe x. Now you want rho q prime. You have to integrate over all x, mu, nu, and p. So only if you did that over an infinite set of slices of the tomogram, that's important, you get the off-diagonals of rho. But look at it experimentally. The experimenter gets very little out of this whole analysis. He cannot do an infinite number of measurements. So it becomes a very important question, particularly these days in the context of machine learning protocols. How many slices are optimal for state reconstruction? And in that case, how do I teach the machine to look at the number of slices that are needed? Now, it is important to note that the completeness of state simply translates to this. This is not enough to guarantee that the reconstructed density matrix is non-negative. It needs to satisfy the Schrodinger-Robertson uncertainty relation. And in order to be a respectable quantum tomogram. Many things can be computed from the tomogram. For instance, the variance for a given theta, the variance of x theta and all the higher moments, the higher order moments, can be calculated in a straightforward manner. And the squeezing properties are therefore directly calculable from the tomogram. It's a nice paper by Wunsch way back in 1996, which gives an elegant procedure for computing objects of this form, a dagger to the K, a to the L, in terms of the tomogram. And you will use Hermite polynomials because, after all, light comes by interpreting the eigenstates of the oscillator as states of the photon and as photon number states. The Hermite polynomials naturally come in. And this is the expression that Wunsch gives. I merely want to point out that you need K plus L plus 1 slices of the tomogram. Remember, this is x theta theta. You will need K plus L plus 1 slices of the tomogram to get an object like this. And you can compute all variances very exactly. There is no problem. But squeezing is not what I want to talk about. I'm merely trying to tell you that several things can be directly computed from the tomograms, avoiding state reconstruction. As I said, before we proceed to bipartite tomograms, you need to worry about the result that I showed by Manco et al. About an infinite number of tomographic slices being needed for state reconstruction. But in practice, will 25 slices be enough? How should they be distributed? I mean, should I choose the thetas in uniform steps, or should I do something else? So now pattern comparison becomes important. If you did something with, say, 25 thetas, you got a tomogram, and then you compared it with the ideal. How close is it to the ideal? How close is it to the ideal qualitatively? How close is it to the ideal quantitatively? Now, these questions become important. But what is it that you're going to compare? You're going to compare probability distributions. They are not quasi-probability distributions. So very nice. I can now resort to classical probability theory. So you compare probability distributions involving the two tomograms for a fixed theta. Use classical quantifiers. So what are these classical quantifiers? Actually, there are a number of such quantifiers given for comparing two classical probability distributions. I'm going to mention just two in this talk. One is the Kullback-Leibler divergence. This is also called the relative entropy. It's a statistical distance. It measures how a given probability distribution differs from another reference probability distribution, which I will call f of x. Now, this is not symmetric in the two distributions. It is not metric. It does not satisfy the triangular inequality. You could interpret it in terms of information entropy. If the relative entropy is 0 between your reference probability distribution and the one that you have created, with a lesser number of slices perhaps, it implies that both the distributions have the same information content. Of course, it's a non-negative function of the distributions. And the definition is here. I want you to look at the notation because later I'm going to introduce similar notations, but in a different context. Case KL in the subscript, of course, stands for Kullback-Leibler, and D is the divergence. And it's an integral over the given range, whatever may be the range, P of x log P of x by Q of x dx. You will appreciate this definition better when I talk about entanglement. Your reference state is P of x. Now, it's obvious that if the reference state were Q of x, the answer is going to be different. So it's just a divergence depending on the reference state. And this can be infinity. The standard example is V of x is a Cauchy density and Q of x is the normal density. Then you can compute that the Kullback-Leibler divergence is infinity. There is also this statistical distance, which is a kind of takeoff on Kullback-Leibler. It's called the Bhattacharya distance. Now, this one is again a method of assessing the difference between two probability distributions. And it relies on something called the Bhattacharya coefficient between two probability distribution functions, P of x and Q of x. The coefficient is this. And the distance itself is minus log of that coefficient. Now, the distance can go between 0 and infinity, but the coefficient lies between 0 and 1. It does not obey the triangle inequality. Its cousin does, and that's the Hellinger distance. But this is a symmetric distribution between P and Q, in contrast to the Kullback-Leibler, where depending on whether P was the reference or the Q was the reference function, the answer changed. Just to get our bearings straight, I want to do a simple example and show you how these distributions may not be very helpful in certain quantum contexts. Example, particle in a one-dimensional box. It's a standard problem. The particle moves freely inside the one-dimensional box and the interval selected is 0, 1, perfectly reflecting barriers at the endpoints. Now, my reference is going to be the normalized positional probability density in classical physics, because inside the box, the particle moves with a constant speed. It does not see any potentials. It does not see any obstacles. And so the uniform density is just 1. And that's independent of the value of energy. I'm going to choose that as my reference distribution. But quantum mechanically, the particle has energy levels like this, as you all know. It's n squared pi squared h cross squared by 2m. M is the mass, and n takes values 1, 2, etc. And this is from the textbook, the normalized positional probability density function corresponding to energy En is mod phi n of x the whole squared, which is this. Now, we want to compute there are two distributions. They're both good probability distributions, or at least density functions. Let us now compute the Kullback-Leibler divergence between them and the Bhattacharya distance between them. The quantum one has an n dependence. Now, if you choose the f of x equals 1, which is the classical PDF as your reference, and wrote it as f log f by g, a simple calculation tells you that the answer is log 2. It's independent of n. For every n, you will get this answer. If you took Gn as the reference distribution, and therefore interchange the positions of f and g, you will get a Kullback-Leibler divergence of 1. So in this problem, I'm unable to see any n dependence if I compute the Kullback-Leibler divergence between the classical PDF and the quantum PDF corresponding to different energy levels. Look at Bhattacharya distance. If you did this computation, you will get log pi by 2 root 2, and that too does not have an n dependence. So it's not very heartening. One feels that the quantum effect is not captured. The fact that the energy levels are quantized is not captured. So does one accept that you can't push classical probability theory and you have to go through messy state reconstruction and all the rest of it? Or is there something else that one can do? So let us see. Now, all these distances do not seem to depend on n. And so the number of nodes does not seem to matter. Let me go to bipartite systems. Let's see if in the context of entanglement, which involves correlations, there is any nice differences brought out by these quantifiers like Kullback-Leibler or Bhattacharya. For a bipartite, my definitions are going to be just an extrapolation of what I did in the single mode case. I will have a θ1 and a θ2, an A dagger whose commutator is 1, a B dagger whose commutator is 1. And it's a straightforward extension. So for a given theta, since we have a complete basis x theta, my tomogram is now a two-mode tomogram, is now a function of x θ1 for a given θ1, x θ2 for a given θ2. And I need to worry about all θ1s and θ2s. In other words, given the two-mode density matrix, it is the expectation value of rho in this state. Manco and collaborators have done a lot of work on tomograms, and it would be very unfair on my part if I don't even mention his name in a talk like this. So let's look at entanglement. After all, we've got a bipartite tomogram. And this is very important in optics because the atom can get entangled with the radiation field. If you have a two-level atom with a ground state and an excited state, it can get entangled with the radiation field. And this also is very amenable for the IBM quantum computing platform because either one photon is absorbed or given, so that's a qubit. And similarly, the atomic state is a two-level state, so that's another qubit. So one feels happy that one can use the IBM platform. One has many other models. Again, the Agarwal-Puri model, which talks of a multi-level atom, an infinite level atom interacting with the field. So A dagger are the field operators, BB dagger are the atom operators. The atom is modeled as an oscillator. It's a nonlinear atomic medium, and this is a simple interaction between them. What's nice in this case is, if you used initially separable states, you put the atom in the ground state and the field in the Fock state 5 photon state, and you let the system evolve under this Hamiltonian. Look at the left side plot. It's the subsystem linear entropy, which is a measure of entanglement. You find things like this. Initially, they are separated. So SLE is 0. And then somewhere at half time, it takes a dip. Of course, at 1/3 time, it takes a dip. And again, periodically, if you didn't have decoherence, the entanglement becomes 0. Very reminiscent of the revival phenomenon, which one studies in single mode cases, except that here we are looking at entanglement. And if you wish, revivals of entanglement. And this is if you use a coherent state, the right side plot, and that does not show such revival patterns. So can one look at these things with Kullback-Leibler and so on? Now, certainly one can capture these things with tomograms, because if you look at, for instance, half time, the two subpacket revival, as I call it, the dip in the center of the left side plot, and look at a time just an epsilon away on this side and an epsilon away on that side, the tomograms show fantastic qualitative changes. So look at the upper tomogram. It's for an initial Fock state of the field, separable state, Fock state 5 and atomic state 0. And the center, look at the top panel. The center is the Fock state 5. Look at the tomogram. It's beautiful. There are 5 vertical lines. That's a 5-photon state. But then you see just an epsilon away. Look at the tomogram. Look at the tomogram and epsilon away on both sides. It looks very different. Where are those vertical lines? They've gone. Whereas here, you know, I mean, if you look at the optical tomogram at a different time, once more, you know, this is when the entanglement takes a dip. On both sides, you see the qualitative changes. The one at the center is very different from what you see on both sides, just at times a little bit away from the actual position of the drummer. So reading of things from the tomogram is an art, and I think it's a very useful art. And but I want to quantify these things. I'm going to use 2 quantifiers, but I'm going to introduce a third one as well, because this subsystem tomographic entropy takes off from the usual Shannon entropy. It's a P log P, which is what I put on here. And you could define it for the 2-mode case. You could integrate out one of the mode and define it for the marginals. And you can define something analogous to quantum mutual information, which has the marginal entropy plus the other marginal entropy. Remember, this is subsystem A and subsystem B of the bipartite, minus the joint thing that I put on here. So this could be a good entanglement indicator, which I compute only from the tomograms. It works pretty well, actually. In several contexts, we have tested this. I'm just saying here that it is analogous to the mutual entropy, mutual information. Now you look at the Kullback-Leibler and the Bhattacharya distances. They are the heroes of today's talk. In terms of the Kullback-Leibler divergence, DKL, now I can write my my kind of a quantifier of entanglement. You see, you have the Kullback-Leibler divergence, but now instead of the function P of X, I will use the 2-mode probability, which I can read off straight from the tomogram. And then you had a P by Q. This is the 2-mode, and these are the factored single modes. So you see, it's obvious. If there is no entanglement, this will become 1. So it is very straightforward to imagine that the Kullback-Leibler divergence itself can be used to study the extent of entanglement. Similarly, you can use the Bhattacharya distance. Consistently, instead of P of X, I will use the 2-mode probability, and the Q of X, I will take the factored probability. So you can define an entanglement indicator, which is what I have put on here. But now, what I did not tell you earlier is it is going to change from slice to slice, because these are probabilities which are very slice dependent in the case of the tomogram. So for every slice, I will define an entanglement indicator. I think that's very nice and very practical, because in an experiment, the experimenter can at best look at some slices which are available to him. Then it is better we talk about entanglement using just that slice. Not for love, not for money can he give you data which you can, simply compare. It's not possible. Most times it is not possible. So this epsilon BD becomes a matter of great significance. Similarly, I can define the Kullback-Leibler again for, the Kullback-Leibler divergence slice by slice. I'm looking at just illustrative examples very briefly. Take coupled harmonic oscillators. Now you see X1 stands for the first oscillator, P1 squared by 2m plus X1 squared, P2 squared by 2m plus X2 squared. Frequencies are the same, and this is the interaction term. Define the standard A and A dagger and write your Hamiltonian. We want to use it later on for nuclear physics and so on. So let's go to center of mass and relative. Put the center of mass at rest. Look at what happens between X1 and X2. All details I'm going to cut out. But I can compute SLE, which is the extent of entanglement between the two oscillators. See here, X1, X2, X1 prime, X2, and so on. And this is the SLE. When the ratio of the frequencies between the center of mass and the relative is 1, it turns out that the two oscillators can separate out and there is no entanglement. You see a 0 for eta equals 1. But then otherwise, when you go to excited states, you see that when you put, I always put the center of mass at rest. When NR is 0, that's the number in the relative is 0. The only way that I can get it is by 0 for X in the for the X1 oscillator and 0 for the X2 oscillator. And therefore the SLE is 0, it's unentangled. These are all entangled. And you see that the SLE is slowly rising. Actually, it is slowly rising, believe me, not perhaps in this plot, but it is slowly rising. The same trend in the Bhattacharya distance. You see the 0 at 1, at eta equals 1. And then for other states with degeneracy, you see the entanglement rising as eta increases. Similarly for epsilon KL, the slice used is the XX slice. So that's why I said the epsilons become important. We've done this for the hydrogen atom problem as well. And we have this very nice result, which one would like to have, of course, that if you use these indicators, epsilon BD and epsilon KL, as the binding energy decreases, as you approach higher and higher states of the hydrogen atom, the entanglement decreases. So that's a nice thing to know. We have also worked with the double well Bose-Einstein condensate model, and I should be wrapping up shortly. And there we have shown that 25 tomographic slices, which are uniformly distributed in theta, are good enough to get hold of the entanglement values. We have worked with the IBM platform and given equivalent circuits for various optics models and seen that the IBM QASM simulator agrees very well, 0.2311, 0.2310. It agrees very well with our actual calculation. The experiment has decoherence, that's why the plus or minus, and we didn't put in experimental losses. We have used tomograms to distinguish between two different biphoton states in an experiment, and these are the two tomograms. And the entanglement between the two states is 6.5 and 5.44 respectively. This is one tomogram for the entangled state. This is another tomogram for the other entangled state. You can see, even looks-wise, they're very different. So I have sung the song of the Kullback-Leibler and the Bhattacharya distance and their use wherever possible. Do not want to go through these things, but just to show that we have worked with other models as well. But I have already given the contents of this in a different context to you. So I'm going to give you the summary and the outlook. The broad theme is how far can you push classical tools in understanding quantum laws? If the classical quantum divide is gray, then this approach should help. The common aspect is probability. So consider an approach based on probability distributions or tomograms in quantum physics. Avoid state reconstruction. States show quasi-probability. Detailing in tomograms is better because investigation can be carried out slice by slice. It's closer to experimental investigations, where only a few slices may be available. The big question, how many slices are needed for a given task? Simple task is pattern reconstruction or similarity between probability distributions. For that, you use distances from classical physics. Still unclear how effective they will be, but in the context of entanglement, they seem to do pretty well. Very important for machine learning protocols and also in pattern recognition in general settings, also in the IBM platform. Other distance measures also need to be examined while comparing probability distributions and their efficacy understood in various contexts. So I think I should stop here. I'm already running 5 minutes late. Thank you very much.
So the floor is open for question.
Professor, I have a question.
Yeah, I'm hearing you.
Thanks for the talk. In bipartite systems, when we are measuring this Bhattacharya distance and Kullback-Leibler distance, if we took the reference as the factored distributions and like.
Yeah. I took the
Right.
separable state as a factor distribution.
Yeah.
Yes.
Yes, right.
Yes.
So suppose if we interchange both of them, the references.
For Kullback-Leibler, it's going to be different. Even as from the very definition of Kullback-Leibler, it's going to be different.
Different, right?
Yes,
So
but
can it still
Bhattacharya will be symmetric.
Okay. Can it still be used as an entanglement
You
quantifier?
can, because that you can. Because you see, these are only, they show trends. An experimenter is normally interested in trends. How does the entanglement change, which changes in a experimentally manipulatable parameter? The actual exact value may not matter.
Okay, but the trend, whether increasing or decreasing.
Exactly. Does it increase? Does it go to zero? In this slice, is there any entanglement at all? Such questions, this is more than sufficient.
Okay. Thanks.
Welcome.
Can I ask a question?
Yeah.
Thank you for your talk. I have one question. So my question is like that. In case of finite dimension density matrix, one can reconstruct elements of the density matrix. So, but in case of a coherent state, dimension of density matrix becomes infinite. So my question is, can we reconstruct all elements of density matrix of a coherent state?
Okay, so basically in a general setting, as in the case of the Bose-Einstein double-well BEC problem that I spoke about, or the Agarwal-Puri model, where you deal with an infinite dimensional Hilbert space, the question is this: can I make do with an optimal number of slices? Because I don't have an infinite number anyway, as you pointed out. It depends on the problem. In the case of the double-well BEC, we could reconstruct. And what is it that you want to reconstruct? You want to know if there is a change in entanglement if you move, if you go on increasing the number of slices. We found in the double-well BEC case that 25 slices was enough. The entanglement extent did not numerically change after that. Therefore, in practice, in that problem, we found that 25 slices uniformly distributed was enough. We could reconstruct the entanglement properties. Now, if you ask me, you might reconstruct the entanglement properties, but can you reconstruct some other properties? You might need more slices or lesser number of slices for that. It is exactly like a medical scan. There are two people, God forbid, who go to the hospital with injured brains. The number of slices needed to do a CT scan on one brain would be very different from the number needed for the other brain. But if all you want to see is a certain property, then you can always find out the number of slices that you need. Now, in machine learning protocols, you could use these distances, like Kullback-Leibler and so on, to see if the qualitative features are the same. And you could try to put in an added constraint, like the extent of entanglement, to see if the quantity does not change with increase in number of slices. Then, as far as that property is concerned, you have done a very successful reconstruction. By the way, even if you're talking about spin systems, how are you going to reconstruct the state of 50 spins put together? Your Hilbert space has become very large. My point is, at some stage, you will have to take the tomographic approach.
Okay, but in this case, will I lose delicate quantum effects such as quantum interference? Because I don't know whether quantum interference will appear in 15th tomogram or maybe 17th.
Okay.
So it is uncertain.
I know some things. If you look at this, for instance, look at the center panel. You see this here? This blob in the center panel, top center panel. You see that intersection between the two strands? those will correspond to interference patterns. So I kind of know from the tomogram itself, for what thetas I get such interferences. And there I will use many more thetas. It is like zooming in a medical scan. You see something terrible happening at some point, you will use many slices near that point. So I will definitely not lose information. I will first look out for those points in the tomogram. The important thing about a tomogram is you first inspect the tomogram. Look at special points in the tomogram, special values of theta. And there you have to use more fine steps. Just like a medical imaging.
Yes, thank you.
Thank you.
But in case of like experimentally, I can identify dipole moment, but I could not quadrupole and octupole moments experimentally. So maybe with this tomogram technique,
I would even suggest the following thing. No, I would suggest the following thing. With your tomogram, try to do this computation, the Wunsch computation. That might help you. I don't know the context, but in general, I get the impression that this might help you. Forget squeezing, but from the tomogram, you can compute higher moments, you see. You can compute higher moments from the tomogram. So you please compute the higher moments from your tomogram. If it doesn't agree with the quadrupole moment, for instance, or the octupole moment, increase the number of slices. Increase the number of slices. And that should help, is my gut feeling.
Thank you.
Yeah, this would be your reference, this Wunsch's paper. This would be the reference, and this is what you need.
So,
May I raise?
Professor Usha Devi has a question.
Okay.
Hello,
Usha.
nice listening to your talk. So
Thank
I just have a curiosity question. That is, if you had taken only Gaussian states and their evolution into Gaussian, you would only require the variances, basically.
Right.
Suppose I have a single mode state.
Right.
So if suppose I take slight deviation, say for example, photon added coherent state is not going to be a Gaussian state, but then I will look at it, there will be slight differences. So such a thing may give you some ideas about how many slices, that is comparison with the Gaussian, where you only need two moments.
That's right.
Very instant.
Right.
And then if you take something else, which is non-Gaussian,
right,
then I do know there is very little difference. So maybe that would give you some.
No, that's exactly what we do.
Okay.
That's exactly what we do. Our reference is the Gaussian state, which is the standard coherent state.
Right.
Yeah, that's what we do.
Yeah, I missed it. Thank you.
Yeah, that's what.
So there is a question in the chat.
There is what?
A question in the chat.
There is a question in the chat. Let me see if I can get hold of that question in the chat. Yes. How the probability is associated with amplitude in the state? No. This is in any general. I'm not being very. What is the word for it? There's nothing esoteric about what I'm saying. You know that if you expand a state in terms of the bases, the coefficients are the probability amplitudes. I'm talking about that. The probability amplitude mod square is the probability density. The probability density integrated over the range of the variable X or whatever you're talking about is the total probability. So when I say amplitude, I mean probability amplitude. When I say density, I mean probability density. And then I talk of the total probability. That's all. Nothing new about it. Just what basic quantum mechanics is. And what if I have a 4-qubit cluster state? Exactly. You're balking at 4 qubits, sir. I'm telling you, what will you do if you have 50 qubits, 500 qubits? There you go. You please look at spin tomograms. and try to read as much as possible from spin tomograms. You have no option. I don't see any other question here. This is what I see.
So see, if any questions are there, please ask, open yourself and ask. Can I ask one question?
Yeah.
See this, typically we say that negativity of the Wigner function, right? How does it manifest through this kind of approach?
No, it doesn't. Not in the tomograms. The inverse Redon transformation brings it. The inverse Redon transformation of the tomogram is the Wigner function.
Okay.
That brings out the negativeness. Yes.
I see.
And that means you're integrating over the tomogram with a Redon transform. You're doing an inverse Redon transformation. That's what brings it. And that is why the rules of classical probability are applied to tomograms.
Okay.
Yeah. That's the idea. Yeah.
So, if there are no more questions, let's thank Professor Lakshmi Bala. And I suggest that please work out all papers because you learn a lot of things. I have learned myself.
I think that's mutual. Thanks a lot, Professor Prashanta. Okay.
Yeah, thank you.
So I will just wait for your next QIQT. Thank you.
Yeah.